Hey everyone, this is Derek. In this video, we're going to look at finding the slope of a line from a graph and then also from a table. So slope, let's take a look and see what that is. So slope is going to be our vertical change over a horizontal change, or you might remember from a previous class, rise over run, or this little symbol you may not have seen before. It looks like a little triangle, but it's delta. Greek letter delta stands for change in, so this reads delta y over delta x, or change in y over change in x. And so here's kind of an example over here. Here's our vertical change. This is our rise. So that would be this piece. Here's our horizontal change. And this is between these 2 points right here. And so that horizontal change is our run. So this distance over this distance, in this case, this would be 2 for a rise. And we're going in positive direction, 3 for a run. So for that table, or for this graph, our slope would be 2/3. So that's kind of the idea of what we're working with slope. Anytime we're working with a linear function, it's going to have a constant slope. So for equal changes in x, we're going to have equal changes in y. And it's not that the x is equal to y's, I'm not sure I said that very well, but for each change in x, there'll be some change in y that's constant over time. So let's see what that looks like with some more graphs. So here we are finding the slope of the line based on the graph. So what you want to do is find 2 nice clean points. So here, this one looks pretty good. And then like I would mess around with all these ones that aren't going through nice spots, but then you come up here and then that one looks pretty good. And then you can just kind of draw a triangle in there. So here it looks like we're going to go up 4, and then we're going to go right 3. And so 4 is my rise, and 3 is my run. So rise over run, that's our slope, or 4/3. And then notice if the slope is going, if it's increasing, if it's getting bigger, we're kind of going uphill as we go left to right, it's going to be a positive slope. If it's going downhill as we go left to right, it's going to be a negative slope. So for this next one, we could just expect that to be negative and write down, our negative sign, m equals negative something. Finding our points, looks like there's a nice one there, and that seems to be the next good one. So this time, instead of going up, we're going right down. So when we travel this direction, we're going from 4 to -1. So -1 minus 4 would be -5. So we're traveling in the negative direction. So this time that's -5. And then we go to the right, that's the positive direction. So that's 1. So in this case, it'd be -5 over 1. We wouldn't want to write it that way. We would just want to say m equals -5. C, so this one is a horizontal line. And so if we kind of look at this and we just pick any 2 points, it doesn't really matter. I'll just kind of arbitrarily pick those 2. If I kind of think, again, rise over run, my rise is nothing, right? Because we're not getting a vertical change. So it's going to be 0. My run, I happen to pick 3, but it wouldn't have mattered, right? 0 divided by any number is going to be 0. So our slope for any horizontal line is always going to be 0. And then we have a vertical line over here. I'll do kind of the same thing. I'll arbitrarily just pick a couple of points. And if I think of this again as rise over run, so this time my rise is, again, arbitrarily 3, but my run, you can see, it doesn't exist. And so now we're getting division by 0, and that is undefined. On the computer, it might be DNE, stands for does not exist, but that's kind of the computer for undefined. Okay, so this next example is also going to be slope, but this time I'm going to do it kind of 2 different ways. I'm going to use this definition where we're given a couple of points and then find the slope that way, and then I'll still go back to the graph like I just did. So here we're finding the rate of change of the graph. Make sure to your answer includes units. Okay, so let's pick 2 convenient points on the graph. I'm just going to arbitrarily grab this one because it's easy to read, and then I'll grab that one next to it because it's also pretty easy to read. And I'm just going to jot those down over here for convenience. So I picked 5 and 80, and then 10 and 120. And then in terms of my units, notice so my input is time. So it's going to be seconds is my input, and my output is going to be meters. So we're putting in seconds into this equation and getting out meters, whatever it is. And then we'll do the units with the slope in a second. So up here we got our formula for slope, y2 minus y1, x2 minus x1. So this is our change in y over our change in x. And so I'll let this be my 2's, my 1's, doesn't matter, but usually let this side be 2's. So then m is 120 minus 80. So y2 minus y1 over x2 minus x1. So 10 minus 5. So that makes 40 over 5 or 8. So 8 is my slope, but it's asking what are the units of this. So again, this was in meters, right? And then this was in seconds. So our slope is in meters per second, so it'd be like a rate of change of velocity. So here, meters per second would be our units. And then going back to what we just did with this, if I just look at the graph, and right here, I can kind of look and go, so what's my change in x? My change in x looks like it's going from 5 to 10, so that's 5. What's my change in y? That's right there. Change in y is going from 80 to 20, or sorry, 80 to 120. So change in y would have been 40, so that I can say 40 over 5, and it's still 8 meters per second. So definitely if you could read it off the graph, that's a whole lot easier than writing down the points and doing all this. But there it is with points, there it is from the graph, same thing. Okay, and the last question for this video is identify a linear function from a table. So the slope of a linear function is constant, right? So what that means is if I have equal space between my x, I should have not necessarily the same space, but I should have equal spaces between my y's. So for equal change in x, I get a proportional change in y every time. So if we look at all these tables, you can see they counted by 2. So that means we have equal change in x. So if our difference in y is the same each time, then that means it's going to be linear. If it's not, then it's not. So looking at this first one, our first change in y, and I'll just kind of do them all right here to scratch work. So we end up at -5. We started at -11. So that would be -5 minus -11, we get plus 11. So that'd be a 6. Between our second 2 points, 1 minus -5, also 6. Between our next 2 points, 7 minus 1, also 6. So you can see for each of these, I would have gotten 6 over 2, slope of 3, 6 over 2, slope of 3, 6 over 2, slope of 3. So this one we would say is linear. This next one, so again, they're all even intervals of x. So here we'd have 4 minus 1 would be 3, 16 minus 4, you can already see that's not going to work, is 12, and then whatever that is, I think 48. So these are, the space between each point is increasing. If we were to graph this, it would be some kind of curve where it was getting, it's growing faster and faster between each successive x. And then here we'll kind of do the same idea. So we'll just kind of go basically like a y2 minus a y1. So -2 minus 6 would make -8. Here, -10 minus -2 would make -8. And then -18 minus, -10, and again, -8. So for that one, linear.